All right, so looking at today's notes, like I said, we are going to be in our NASM today, which is exciting. It is where we're going to sort of take their approach to the kinetic chain. So it'll be a little bit less detailed, but at the same time, you'll notice like one of the things that NASM puts a lot of emphasis on as they're sort of going through this chapter, is the fact that all three of these systems are very interconnected. So they really put like a lot there. But what's nice is, like I said, you've all heard this information before, especially those of you who are in your second and third mods. You guys are definitely familiar with this information. But again, always kind of good to review here. So, because this is honestly, like when you look at your NASM exam blueprint, this is, I'm just going to pull this up here. So this is like a detailed breakdown of how your questions work. 15% of it is going to come from basic applied sciences and nutritional concepts. So I would say that probably 10% of that is the nutrition stuff. And then, or I'm sorry, 10% of that is probably the basic science stuff we're talking about today. And then 5% it would probably be nutrition. They don't do a really super detailed breakdown of that. But that is sort of domain one. Then we'll get into client coaching after this course is over, actually. Assessment, we always cover like, sort of as we go, but then also we have a whole mod dedicated to it. Program design, we cover constantly. That's all the program design classes. And then there is the professional development stuff, which, fun fact, is not all in your textbook. Arlene, we just had a conversation about this the other day. There are a couple questions. The only thing that is not in every question on your test will come directly from your textbook, except for like 1 or 2 questions, which are found in NASM's handbook. And they'll give you the handbook when you actually get you schedule your test, which is kind of a weird way to do it. But, that's sort of how they're ensuring. To be fair, we've covered the handbook information. The questions are literally like, what do you need to get, to your CPR, and how do you stay recertified? That stuff that isn't in your book, but is in the handbook. But yeah, let's take a look. I'm like off on a tangent for test prep here. Let's take a look at chapter 2 here, right? So we are looking at the basic science of everything. So purpose of today's lesson, we want you guys to have a good fundamental overview of the entire kinetic chain. And we want to understand how all three of those systems sort of work together to function to create actual human movement, right? Oh, and then one last thing I do want to mention today. You will notice that even though the slides are relative, there's not very many slides. These notes are kind of everything. I kind of took, like, it's almost like everything in the PowerPoint. So it's almost as if the notes sort of translated directly over from word for word from the PowerPoints. But it's meant to sort of summarize everything we've talked about over the last couple of days. So if you've been, paying attention and like, you're just like, man, there's no way I need to know this much about like chemistry or cellular biology. You're not necessarily too far off on that. But this chapter is going to sort of like, it's going to give you the sort of Spark Notes version of everything that we've been talking about. So we want to understand the function of the nervous system, skeletal system, and muscular system. You will notice that endocrine system gets exactly the same treatment it did last time, like we did on Friday, where it gets very skipped over. Fascinating system, very fun to talk about. Unfortunately, not super important to NASM. And then we're going to describe how they adapt and respond to stress. So the human movement system, like I keep saying kinetic chain. Which one is it? It's both, right? Like both of those definitions kind of work. I personally like kinetic chain because the part of that phrasing that I like to focus on is the fact that it is a chain, right? Like, and whenever there's like a link in a chain that's messed up, all of it's messed up, right? Like you're only as strong as your weakest link, right? That's the phrase. I hope that's not one of those phrases that has like way more to the phrase that we've just sort of gotten rid of over time. But yeah, you're only as strong as your weakest link, right? And so when we think about the kinetic chain like that, you know, we start to understand it's like, oh, if my skeletal system is out of whack, my muscular system isn't going to be able to move properly. And that's going to adjust how my nervous system sort of learns this particular movement, right? So let's say you have like, actually, question for anybody in the room. Tight calves are probably one of our most common problems, but chime in if you feel like this is you. Does anybody, when they're stretching their ankle, stretching their calf, feel specifically a pinching sensation in the front of their ankle? You feel like a pinch as you're sort of trying to bring your shin forward. It feels like your ankle's getting pinched.
Yeah, I also get that feeling if I'm kind of walking up like a semi like slanted type of heel, like a hill in a way. I feel like a tension in the front of my shin.
Yeah. So the tension can be fine. That could just be like the muscle trying to keep up. So when we look at like the movement, right? We have like dorsiflexion and plantarflexion, right? Those are the two things your ankle's supposed to be able to do. So you have plantarflexion. Good Lord, look at that plantarflexion. That is a dancer's foot. You can see this crazy like major point here, right? That's plantarflexion. You're planting your toes, right? And then there's dorsiflexion, which is bringing the ankle up this way. So Alyssa, what you might be feeling is just the muscle that's responsible for dorsiflexion. That's going to be your anterior tibialis muscle. Could just be
normal.
What's that?
Is that normal for it to feel like? Well, it doesn't really feel that way anymore now that I'm more active, but before it would feel like that a lot.
Yeah, normal is a tough word to place on it, but I would say like, you know, form following function, right? I would say that like if that muscle is having a hard time keeping up, you're going to feel it more, and then that's going to draw your attention to it, and so it will feel quote unquote weird, right?
Got it.
But there's a lot of things you can do, right? You can do like resisted dorsiflexion. Go get yourself a resistance band, tie that resistance band to the wall, tie it to something heavy, and then just pull it back like this. And that little like toe pull can strengthen it. And anytime you do like a balance exercise, right? Anytime you do like a single like balance exercise, right? Pull that toe up rather than letting it hang kind of loose. And that can really help you like sort of strengthen that. And honestly, it goes away very quickly. And then lots of balance exercises eventually get you there. And you just want to always make sure that you're, you know, it's funny. Alyssa, did you dance as a kid, or I don't know, as an adult? Did you dance like
yeah, in like middle school I did a lot of like drill team and stuff like that.
Oh, drill team. Okay, yeah. I was gonna say like usually it's like jazz dancers or classical dancers.
Oh wow. To have it?
Yeah, because they're toe pointers.
Yeah, I think maybe because the placement, I was always like the split person and stuff like that, so I did have to have a lot of proper form.
Yeah. So I'll say, like this girl here, she's doing like a great single leg balance exercise. I love it. She definitely has the wrong arm forward. It should 100% be this arm here, and this one should be down her side. She's doing the Frankenstein walk right now. But the worst thing about like this form that I'm seeing right here is that she's got a lazy ankle. I would say, hey, pull that toe up. Also switch your arms, lady. If she were my client. I mean, I get it. They're doing it because of the picture, but guys, never move right arm and right leg. Otherwise, you are literally doing the Frankenstein walk. You wouldn't walk like this. Like, it's very weird looking. Anyway, yeah, so I'm seeing it all over the place. Look at this, lazy toe, right? We don't want a lazy toe. We want to have an active toe. So, but getting back to the pinching thing. So one of the things that can happen, in the ankle joint, right, is you can experience a little bit of what's called translation. So translation isn't in your textbook or anything. It may be in your corrective textbook, but what it is it's kind of where like a bone, it's like the bone's not dislocated, you know, it's not subplexed, it's not out of alignment really, but it is just not in the optimal placement. It's just not perfectly where it should be, right? So sometimes one of the things that we'll see That's like a freaking pin. That's not what I'm talking about. Every now and then you'll just see a little bit of anterior translation. So what'll happen is this bone right here, right? That's your tibia. That's your shin bone as it comes down. It'll just through like habits and overactive muscles here and there, it'll just get pulled a little bit forward, just barely. And then this muscle right here, this is called your talus. And actually, let's just try that. Your talus there sort of slides forward in response because the talus is meant to be there to actually act as like the base of support, right? So the talus is where your tibia sits, right? So if these both sort of move forward a little bit, when you try to like roll, pull your toes this way or roll your shin forward this way during like a squat or a low lunge or something like that, you'll get this like pinching sensation. And one of the things you can do is you can do a posterior translation of that talus and you can actually see it here. This is Brent Brookbush, by the way, who, if you want to follow a physical therapist on YouTube, this is the guy. And what he's doing is he's actually doing a posterior translation. He's literally grabbing her talus and grabbing it with his hand and just pulling it straight back. And he's going to slide her bone back into optimal alignment. And then she's going to pull her toes back and she won't feel that pinching sensation. There's also a way to do this with a band. Band translation ankle stretch. I know I'm kind of on a tangent here, but you take a band and you tie it behind you, and then it goes down and behind, right? And what you do is you just put it on the talus. Don't put it on the tibia, put it on the talus, which is like the top of the ankle, but not quite the shin. And you pull straight back, and you will notice how much further your toe can go. Alyssa, if you get that pinching sensation, I'll bet you could literally do that right now. Like, I don't know where you are right now, but like literally, if you've got like an elevated surface, go like
Take
this.
my daughter to daycare.
Okay, well, yeah, then don't do this right now. But like literally, you can grab right about here, and then all of a sudden your shin will just go. You'll feel it. You'll feel like you're able to waist stretch, and you'll feel a much deeper stretch back here as well, because you're going to get a range of motion that you're not normally used to feeling. So that's a
good stretch for that feeling.
Yeah, it's great. You'll feel that, particularly with all this bending action and like this bent knee joint, it'll be the soleus, not so much the gastrocnemius, but still a very good stretch. And that's a great way to sort of get your body to go, holy crap, I'm keeping this bone in the wrong place, right? So the reason we get that pinching sensation, guys, is because like the skeletal system is slightly out of alignment, right? Now the muscular system can't recruit the muscles properly. So we start to feel, sort of pinching. We start to feel like these sort of awkward movements, right? Then let's say we exercise regularly, right? With that pinched ankle, somebody tries to squat and squat and squat, and they're just leaning forward a little bit. They're doing that excessive forward lean because their ankle can't come back. They have to sort of drop their chest down. And now they're learning how to squat the wrong way in their nervous system. So the skeletal system affected the muscular system, which affected the nervous system. Again, it's a chain, right? If you just have poor movement patterns, your nervous system doesn't know how to do things properly. It's going to move the muscular system it's going to tell the muscular system to move the wrong way. And then that's going to move the skeletal system the wrong way. And that will also lead to like impingement and like all kinds of other problems, right? Or if your muscular system has like a tear in it, your nervous system is going to be very sort of sensitive to it. And then that whole thing's going to like move you into a different alignment to avoid the aches and pains. Now your skeletal system is, again, moving the wrong way. So if any of the links are messed up, they're all messed up, right? And that sort of rounded approach to kinesiology, that rounded approach to like understanding human movement is at the core of what we do as personal trainers, right? So all three of these systems have to work together. So I personally like the kinetic chain more than I like the human movement system. I like the human movement system too, because it's like, oh, which system is that? It's like, well, it's actually three, like I think that's descriptive as well. But I love the term kinetic chain because kinetic means forces and chain means links, right? And so like if one of them's goofed up, they are all goofed up. So they have to work together. We have to make sure they're all in alignment. So let's go ahead and quickly review our nervous, I say quickly, but obviously I just took like 20 minutes to talk about like ankle impingement. Let's take a look at the nervous system, right? This is obviously a specialized system containing all kinds of really cool cells called neurons that are, and this is NASM's definition, providing a communication network throughout the body. So I like the term communication network because like, you know, it's information going in one direction, but it's also information going back in the other direction, right? So like, you know, that is both of those two systems sort of like coming together, right? One direction and the other direction, they both come together. And that is how we get that communication network, right? So, you know, you have to be able to gather information from your environment, get it to your brain. Your brain can interpret it and send the information right back. So if you were to give me, so I know that I shouldn't admit this as somebody who talks about diet and nutrition all the time, but if you were to give me like a bite of like kale, there, I hate it. I don't love kale. I'm not afraid to admit it. But if you were to give me a bite of it, right, what would happen? Sensory information would go up to my brain. Like if I was like blindfolded, right? Sensory information would go up to my brain, and my brain would go, no, last time we bit into something, oh my God, it's kale. And then it would hit the freaking warning button, and then that would come back to me and I would go, bleh, right? So information in, process, information out. That is literally how our nervous system works. So that's a communication network, right? It's information going in both directions. So in order to understand that, we do have to sort of look at sort of how we divide this whole thing down, right? We have our central nervous system. That's going to be your brain and your spinal cord. That's your CNS. And then you have your peripheral nervous system. That's all of the peripheral nerves as well as the spinal nerves that are branching out from the central system. That's your PNS, right? So that is what's creating this sort of network, right? The central system, the brain and the spinal cord, that's responsible for all the like decision making. That's responsible for all of the like processing, right? The memories and things like that. We talk about the idea of like muscle memory, right? Your muscles don't have like a little brain inside of them. They don't have muscle memory, but your actual brain has communicated with the parts of that muscle that have done some type of action before. And so, yeah, like it becomes like essentially muscle memory because like, it's like, you know, when I go to throw like a baseball or something, like I haven't played baseball since I was a little kid, but like I still remember how to do that pretty effectively, you know? And so like if I needed to like do that, my nervous system is going to go, oh, well, we haven't done this in a while, but you know, dust it off. Here we go. You need to use this neuron to that one, to that one, to that one, to that one to control that muscle to do that. And it just sends the information right out, and hopefully it's not too bad of a throw. There's a reason I was in the outfield though. Which outfield is a lot of action like later on. In Little League, not so much. Yeah, Simon, you're like, outfielders have a lot of work to do. Yeah. Not in Little League.
Like last resort, we're the backup.
Yeah, exactly. Yeah, I was the one in charge of like running to first base when there was a bad throw. But yeah, so I literally haven't played baseball since I was that. I probably haven't touched a baseball bat in probably 20 years. So three primary functions here, right? This is the fun part. This is what we sort of like, this is sort of what we set up last time, but we didn't necessarily talk about this. NASM is going to spend much more time here talking about the function of our nervous system. Your nervous system is going to function in three primary ways, right? So it's got sensory jobs, integrative jobs, and motor jobs. So again, we're looking at this in terms of like, you know, a communication network, right? Let's go back to the kale analogy, right? Kale hits my taste buds work with my nervous system to gather information. That information goes up to my brain. Then my brain is going to interpret the taste and chemicals that are in that food and go, I think that's kale, gross, right? And then that information is going to come back down, and the motor response is going to be me going bleh, and spitting it out of my mouth. Right? Like that is the three sort of like main primary functions of your nervous system. So you've got the sensory function, which is your nervous system's ability to sense changes in either the internal or external environments. Let's use a different example. Let's say you place your hand on something really, really, really sharp, right? So that information is going to get gathered in, let's say, the palm of your hand, and it's going to travel up from neuron to neuron to neuron to neuron to neuron to neuron to neuron until it gets to your central nervous system, right? Either the brain or the spinal cord. Now, if you touch it lightly and it's like, oh, that was kind of dangerous, right? It'll take the time to go, well, it's not too painful. The signal will travel all the way up to the brain, and the brain will go, yeah, move the hand away from that, right? But if you did it, if you like stabbed it in there really quick, and you have that like kind of knee-jerk reaction, in this case, it would be like elbow and shoulder jerk reaction, right? That would actually be, it would travel from neuron to neuron to neuron. It would get to your spine, and your spine is going to make the simplest, quickest, fastest decision without even letting it travel to the brain. And eventually your brain will sort of pick up on it afterwards and be like, what happened? Oh my God, yeah, be afraid, you know, like, but your brain kind of takes a little bit too much time to process stuff. So emergency situations are handled by the spine. So sensory information is going to travel from place to place to place to place to place, gathering intel, right? If you eat food, right, and that food drops into your stomach acid is going to start getting made and produced because stretch receptors in your stomach will be triggered. So that's your sensory information working with your nervous system, right? So you trip those sensory receptors so the information can go up to the brain and say, hey, brain, we just got a whole bunch of stretching that happened in the stomach. The stomach's filled with food. We need more stomach acid, right? So then we have like integrative function. Integrative function is, it's very hard to talk about these without like sort of blending one into the other. But like integrative function is the ability of the nervous system to analyze and interpret the information to allow for the proper decision making. And then it can recruit the appropriate response after that, right? So again, kale comes in, my brain goes, that's gross. That's integrative, right? It's like, hey, the last time we tasted all these chemicals together, oh my God, it's kale. You know, like that's the integrative approach, right? You touch the sharp object, your brain goes, yeah, the last time we touched something like that and we tripped those specific sensory receptors, we tore the hand open, right? That's not good. So integrative function is like running things past experiences that you've already sort of like gone through in order to recruit the appropriate response. Again, now that the stretch receptors in the stomach have been triggered, the integrative function is going to go, oh, we should make stomach acid, right? And then all it has to do is actually make it happen. So then motor function is the neuromuscular response to that. So, you know, in the kale, like the response to that is bleh. In response to like the sharp object, it's to move the hand away. In the response to food dropping into the stomach and stretching the stretch receptors and needing to process that, the motor response is to squeeze some glands to secrete some stomach acid. So that's the neuromuscular response, right? So motor units in the hand are recruited to pull the hand away, right? Let's go ahead and use an example. Let's put all this together in an example that actually makes sense to us in like a gym environment, right? So let's say you are doing some bicep curls, right? You got 2 dumbbells in your hands, you got 2 feet planted on the ground firmly. So what's going to happen is the sensory information is going to come in from all of the different mechanoreceptors throughout your nervous system. And information is going to come in and say, hey, we've got about 15 pounds in each hand, right? So your brain's like, all right, well, then this is how much muscle we need. So the information comes up. Your brain says, this is how much muscle we need. It sends it back down and it recruits the appropriate number of motor units in order to move 15 pounds worth of weight. If it was 20 pounds, it would recruit that much. If it was 10 pounds, it would recruit that much. So that's information coming in, being interpreted, and a response going out, again, like a network. So let's say all of a sudden you stop doing regular old bicep curls with both feet planted on the ground, and now you start doing single leg bicep curls, right? Single leg bicep curls are going to, you know, you standing on one leg, and now there's a lot more sensory information coming in. So all the information coming in is like, oh, we're here. No, wait, we're here. We're here. We're here. We're here. We're here. Right. And your brain's trying to keep up. It's like trying to be like, all right, well, we need to recruit these muscles to keep us balanced. Oh, now we're tipping this way. We need those muscles to keep us up. Now we're tipping this way. You know, like your brain is just constantly sending information back and forth, trying to like get into balance. And eventually it'll find the perfect optimal alignment, right? Like your brain's like, well, a little bit of that worked, but you know, oh, that was a little bit effective, right? And then it starts putting them together. It's like, what if we try this? Now we're in alignment. Now we're in balance, right? And that's why you start to get better at balancing the more you sort of practice it, right? That's all of the sensory information coming in and your brain learning how to like recruit things the right way. This is why we start our clients when we look at NASM's OPT model. Okay, that's backwards. When we look at our NASM OPT model, we start our clients at the bottom of this staircase in the stabilization level, right? And so stabilization is all about picking single-legged, wobbly, unbalanced exercises because it produces maximal sensory information. Your brain is going to learn how to do movements the most effectively when it does them in an unstable environment. You are sending the most amount of information in. So the integrative part of your nervous system and the sensory part of your nervous system get to work in just a maximized sort of environment here, right? And your brain gets to try all kinds of different motor functions to sort of get you back into alignment to maintain that balance. And if you can do it and it can learn how to do it properly, you're going to be really great at those particular movements. Because if you can do a single leg bicep curl, I promise you, you can do a safe, effective, heavy, regular bicep curl or seated bicep curl, you know? And that's sort of like why we take this approach and why we spend so much time sort of talking about the nervous system. So how do we sort of summarize all this and sort of put it together in a really nice, neat package with a really nice looking bow? Well, this is where we start talking about the concept of proprioception. So proprioception, I would argue, is probably the most important concept on today's lesson. And it's everything that we've sort of been describing so far, right? Proprioception is, by definition, your body's ability to sense the relative position of adjacent body parts. That's a technical definition. The other super technical definition is it is the cumulative neural input from all proprioceptors throughout the body. Yeah, that's great, but that is like a lot of technical, mumbo jumbo in my opinion. So how do I like to summarize what proprioception is? It's your body's spatial awareness. It's your body's ability to know what position an arm is in or a hand or something like that. So let's say, for instance, you've got your hand like behind your head like this. Now, how do I know that I'm wiggling my fingers right now? Right? How do I know that this is actually happening? Now, you might take a really reductive answer and say, you know that your fingers are wiggling because you're the one telling them to wiggle. Yeah, sure. That's actually not untrue and is correct, but it's a very reductive sort of approach to it. So when I'm wiggling my fingers with, I can't see them. I don't know about you guys, but there have been plenty of times where I've told someone to do something, but they haven't done it. So how do I know that it's happening? How do I know that I am telling my fingers to wiggle, but how do I know that it's actually getting done, right? Well, it's a communication network, right? There are stretch receptors, there's tension receptors, there's length receptors. All of these different receptors, pressure and acceleration and deceleration, all these little receptors that live in my hand, in between all my joints, in the muscles of my hand, right? And whenever I move them or stretch them, information is going to travel up to my brain and say, let's just take a look at this finger joint right here, for instance, right? So right now, that's pretty much as stretched out as it's going to get. Now, obviously, I can sort of overstretch it by pulling it back this way, right? And I can contract it by pulling it down this way, right? So I've got control over it in all these different ranges of motion. There's a big difference between what this feels like and what this feels like, right? So the information's coming into my brain saying, hey, I'm at this length, hey, I'm at this tension, right? Let's use the bicep as an example here, right? So right now, my bicep is pretty much stretched out as far as it's going to go, right? I can't really take my elbow any further than this. So my bicep is at maximum length right now, Okay, it's fully stretched out. Whereas my tricep is sort of at minimal length right now. Like it is on the opposite side of the joint. It's as contracted as it can get right now. My tricep is fully shortened. It can't really go any shorter than that. So the bicep is fully lengthened. The tricep is fully shortened. So what's going to happen is information is going to travel up from the bicep saying, hey, I'm at pretty much like maximum length right now. And information is going to come from my tricep and say, hey, I'm pretty much at minimal length right now. So then the other information going in from the bicep, right, is that because it's fully stretched out, right, the tendons and stuff, they're getting pulled apart, right? So sensory receptors are saying, yeah, there's a lot of tension on the biceps right now. And then the same thing is true of the triceps, right? The information is coming in and say like, hey, this is how much tension is in the muscle right now. So now I've got one system saying what length the muscle is in. I've got another system saying how much tension is in that muscle and whether or not it's going to rip off my bone, right? And that information is going into my brain, and my brain goes, okay, that means that we must be in a arm locked position, right? If I go like this and I'm halfway bent, right now my bicep and my tricep are pretty much at equal length, sort of split between the two at like 50% max length. This is ideal, right, in my nervous system's eyes, because there's very little tension, there's very little length, the muscle's not being overstretched, and it's not being pulled on the tendons. So this is the position that's like nice and safe, right? The same thing would be true if somebody had like rounded shoulders, right? Let's say I've got an overactive chest muscle. I do way too many push-ups. I do nothing but chest exercises, and I never stretch my chest. I slouch and hunch whenever I'm sitting. And so like eventually my brain sort of gets used to this position here because the muscles in my pec contract and then they don't want to let go. They're lying to my brain saying, hey, I'm at full length. I couldn't possibly stretch any further than this, right? Which is obviously not true, but like that's the sensory information coming into my brain. It alters my proprioception. And my brain goes, oh, well, I guess since we're at full length now, when we couldn't possibly stretch any further, we're just gonna have to leave it there, right? So that's where sensory receptors start to really goof up our proprioception. And that's something we're gonna talk about a little bit later when we get to the muscular system. So proprioception is a really key concept in avoiding injuries and stuff, right? Going back to what we talked about earlier, I assume, Alyssa, that your ankle feels normal 99.9999999% of the time. But then when you get that pinching sensation in there, right? That's when you notice it's a little bit off. Well, that is because it's slightly out of alignment, but your brain has sort of gotten used to that movement. And so it has altered proprioception like slowly over time. And now your brain thinks that that's a neutral position. I know a lot. Oh, sorry, go ahead.
I was just gonna say like, okay, like that makes more sense now. I understand why.
Yeah. So it's altered. So I know a lot of you guys, when we've been in the gym doing our workouts and stuff, we'll do like a calf stretch, and I've come around the room and been like, hey, you got to straighten your ankle out, right? And you're like, it is straight. And then all of a sudden you move and you're like, that's straight. And you look back and it is, but it feels like it's not. That's a classic. That's altered proprioception. So probably one of our most important terms here, right? So it becomes really important for us to train using sort of what we would call a proprioceptively enriched environment. Basically, it just means like an unstable, wobbly environment that makes you have to use your maximal sensory information. All right, so zooming in real quick, just to give us some perspective here, we got to take a look at the neuron. We know that the neuron is the functional unit of the nervous system. We got a little biology here, right? So we use neurons to sort of communicate, right? There are literally billions of them throughout your body. 86 billion in just your brain by itself. So functioning in the nervous system is going to be that neuron, and it is going to have all the normal cell characteristics that we normally see, right? We're going to see the cell body. Yeah, it's going to have mitochondria in it. It's going to have lysosomes and centrioles. It's got a nucleus, it's got all the normal stuff, right? But again, with form following function here, we know that it also has to have, specific fibers that make it unique, right? And so that's where we've got some special fibers here on neurons that we're not going to find in other cells. And so we've got these little fingers that branch out from the cell body. Those are called your dendrites, right? Dendrites are going to gather information from like other neurons and stuff. So they are actually sort of providing the network from neuron to neuron to neuron, or maybe neuron to muscle or neuron to gland or whatever, right? So dendrites are the little fingers, and then the axon is the tail, right? This big long tail here that allows us to sort of cover a lot of ground whenever we're looking at a neuron, right? So the tail allows you to actually synapse because it's got more sort of fibers at the end of that tail. So this dendrite here is going to gather information. It'll go into the cell body, travel down the tail, and then it'll sort of like interact with some, muscle or gland, like I said. Those are sort of the different type or pieces of an individual neuron. Now, there are going to be different types of neurons in the body, right? We talked about this on Friday. You've got sensory neurons. Sensory neurons are neurons that transmit impulses from an effector site to the brain, right? They're in charge of sensing stuff, right? So when you touch something, sensory neurons are getting that information to your brain. And then interneurons are actually going to, allow that to actually travel. So like you do have to get it from the hand to the brain. There's not one neuron all the way from the brain. So it goes from neuron to neuron to neuron to neuron to neuron and neuron until eventually it gets all the way up to the brain. So sensory neurons gather the information. Interneurons sort of carry it from place to place to place. And then once your brain does integrative function and says, well, this is the response we should make, it sends the information back through motor neurons to recruit the appropriate like muscles or glands or whatever in response, right? So like when we look at like, let's probably just do that. So let's say the information comes from like, something like a pain receptor, right, on the skin, right? So you poke something. So sensory neurons travel up to the brain, and it goes from neuron to neuron to neuron to neuron to neuron. But I guess the brain goes, we need to recruit the arm, right? And so then it sends information back down and recruits the motor units. Those are the motor neurons that are carrying that. So sensory neurons go towards the brain and motor neurons go away from the brain. So looking at the divisions of our nervous system, now we need to sort of talk about like how our body can go on autopilot. Well, we've got the central system, which again, that's the brain and the spinal cord. And then we get the peripheral nervous system, which are all of the nerves that are branching out, right? So from the brain and the spinal cord, look at all these nerves that sort of travel out, in these like big bundles to cover the entire body, right? Kind of looks like this. You ever look at the bodies exhibit? It's kind of amazing. They've pulled out good sections and sort of splayed that out, right? So you can kind of see everything there, right? So you're going to have a whole bunch of different pairs of like cranial and spinal nerves. Those spinal nerves are going to sort of branch into different sections. That is where you'll see like your different vertebrae. So you have like all of your cervical vertebrae, your thoracic vertebrae, and your lumbar vertebrae, and at the very bottom you have like your sacrum, right? And so like that's where all those like sort of like highways. Think of them as like exits on a highway. So your central system is responsible for all the decision making, and your peripheral nervous system is responsible for carrying out those decisions, but also gathering the information. So when we think of like sensory neurons, they're traveling through the peripheral parts of our nervous system. When we think of motor neurons, they're traveling out through the peripheral parts of our nervous system, right? So like my brain makes the decision, travels down the spine, and then uses the peripheral system to recruit the appropriate muscles. Or if I touch something, the information travels through the peripheral to get to the central. But obviously, like we need to divide that peripheral system into two different sections. We have been talking about the stuff that's voluntary, like recruiting a muscle on purpose. That's part of your somatic nervous system. That's voluntary, right? But you also have all the automatic stuff that you don't want to think about. Like my heart's been beating this whole time. Your heart's been beating while you've been listening to this. You don't have to think about beating it consciously, right? thank goodness. That's your autonomic nervous system. That's the involuntary stuff. And you may think that like, well, we don't really need to talk about that as a like we're only training the somatic stuff, right? I'm voluntarily lifting weights. Yeah, absolutely. But you are having an effect on the autonomic parts of your nervous system. Like the more you exercise, the stronger your heart gets because you are teaching it how to autonomically recruit and keep up with the stress that you're creating with your somatic nervous system. So you start running. All right, David, you went for a run this morning, right? So you used your somatic nervous system to voluntarily start running, but the byproduct of exercise is lactic acid. And so there started being some chemistry changes internally that made your blood more acidic, right? So then the autonomic parts of your nervous system were like, woof, man, the blood got really, we should pump some oxygen in here in order to like lower the pH and like get us back to neutral, turn that lactic acid into energy rather than just letting it sit here, right? So the autonomic nervous system started recruiting. That's your involuntary system, right? In order to like increase your heart rate, open up the blood vessels to the muscles in your legs and stuff. And that allowed you to sort of like respond to the amount of stress. So yeah, we spend most of our time using our somatic nervous system, but we are in a roundabout training our autonomic nervous system. I always think about like the somatic nervous system as like the classic approach to like, like learning karate. Like it's like a karate instructor being like, you're gonna punch like this and like rotate and then like pull it back, right? Like it's like the classic stuff. But then like I always think of the autonomic nervous system as like the Mr. Miyagi approach to karate training, right? Like show me wax on, wax off, and it's like you learn how to block. It just kind of happens automatically. I really hope that most of you guys get that reference. If you haven't seen The Karate Kid, and I mean the good one, you gotta watch it. It's amazing. It's like, show me paint the fence. He's like, block high, block low. It's the best. True story. My dad and I had like a tradition. We would watch like Rocky, and then we would also watch The Karate Kid right afterwards. And like Rocky was for him, and Karate Kid was for me. But really, they were both for me. So that's the autonomic approach, right? It's the stuff that sort of happens automatically, sort of in the background there. Now, there is going to be one more division within the autonomic system. We are either going to speed things up or we're going to slow things down. That's the sympathetic versus the parasympathetic system. So, David, when you started running, your sympathetic nervous system, that's your fight or your running flight system, right? It started recruiting all the muscles to help you either fight or flee. And so, again, dilating blood vessels, speeding up the heart, all the things that sort of amp stuff up, right? The parasympathetic system is what happened when you calmed down, right? You were talking about how you popped a squat, sat down for a few minutes, kind of cooled down a little bit more than you maybe should have, right? Well, yeah, that's your autonomic nervous system's parasympathetic side that was sort of calming you down. It's like your body goes, oh, we're done exercising, great. And so it closes those blood vessels, slows the heart rate down, sends all the blood flow to your digestive system, because like chances are the reason you were just running is because you were running down and hunting some kind of animal, right? And so now that you got it and everything is calm and relaxed, let's speed up the digestive system and get that kicking into gear so you can process said animal, or, protein shake in our case, right? So that's sort of how we use our autonomic. There's either the fight or flight system or the rest and digest system, getting you back to normal. And that's one of the reasons why it's so important to like cool down after exercise, right? Like by cooling down, you are telling your body that the fight is over. We won. Let's relax and get back into like muscle building mode so we can do it all again more effectively next time. And that's, everybody likes to skip their cool down, but it's one of the best ways to sort of like get that calming sensation that we get after we leave the gym. We want to feel, the endorphins, we want to feel relaxed, we want to feel like successful, so we're going to use our nervous system to be able to do that effectively. But you can't really do it consciously. You have to train it, it's like, training a dog. All right, so next thing we're going to talk about, remember I said proprioception is probably the most important concept. Well, let's take a look at how our nervous system works with our muscular system to have that proprioception. So I was talking in general about sensory receptors that were sensing the length and tension of muscles. There are specific names for those things. So the sensory receptors that we've got, these are what they are by sort of big definition. All the sensory receptors running throughout your entire body, they're specialized little structures designed to turn like environmental stimuli, touching, stretching, sensations, pressure, taste, all of those things into information that your brain can interpret. So there's all kinds of sensory receptors out there. There's nociceptors, those are pain receptors. Those don't kick on until they hit like a certain threshold. So like nociceptors are totally inactive until you poke hard enough, and then you're like, ow, and that's a nociceptor, telling your brain like, hey, this is going to hurt us, You got chemoreceptors. They're the ones that, David, those are the ones that sense how acidic your blood is. Chemoreceptors are the things that allowed me to sense like, woof, that's kale, smell, taste, things like that, right? Those are chemoreceptors. They sense chemicals, right? You got photoreceptors. Those are the ones in your eyeballs that are responding to different wavelengths of light, which is pretty cool. But the ones that we're going to spend most of our time talking about are mechanoreceptors, right? These are sensory receptors that sense physical changes, touch, pressure, accelerating or decelerating, right? The amount of stretch on a muscle. That's all the information that we've got there. So there are going to be sort of three main mechanoreceptors that we spend our time talking about in the realm of training, right? So one of them is going to be muscle spindles. So muscle spindles are these little sensory receptors that live in our muscle. They coil around our muscle, actually. And their job, that's a way better picture. Their job is to sense how stretched out a muscle is, right? So a stretched muscle is going to pull on the mechanoreceptor and sort of pull it apart, kind of like a slinky, right? Or a spring. And so the information is going in like, whoa, we are being stretched, right? Or if it's fully contracted, right, that information is going to go to the brain and say like, hey, like what kind of as contracted as we could possibly be right now, right? So you think about like stretching it out, right, versus like coiling it up. So that's sort of how muscle spindles work. This is how your brain knows what position your body is in. When the muscle spindles are saying this muscle is this length and that muscle is that length and that one's that length, right? It means that you are doing, you're in this position or that position or whatever, right? That's information coming from muscle spindles, but there's also information coming from Golgi tendon organs. So a Golgi tendon organ actually lives within the tendon of our muscles. So this doesn't live in the belly of the muscle the way a muscle spindle did. This actually lives just directly in the tendons. And their job is to sense like, hey, the collagen proteins that are holding this muscle onto the bone are about to lose their grip and your bone is about to become detached from your muscle, right? Like that's what these sensory receptors do. So your Golgi tendon organs live in the actual tendon and their job is to sense tension. So the muscle spindles sense length, the Golgi tendon organs sense tension. And for the record, while they're doing all this, they are also in charge of sensing how fast these things are changing. So they are sensing the rate of tension change and the rate of length change. If you change both of those things very quickly, your nervous system will probably freak out. So if you over lengthen a muscle, its response is going to be say, hey, let's not lengthen it that much. And it's going to pull back, right? It's going to shorten the muscle. Or if there's a lot of tension on the muscle, the response is going to be, hey, let's relieve that tension. Let's shorten that muscle, right? Let's pull and contract that muscle, right? So like those are the two safest things to do, because if you pull it and shorten it, it's not going to be at maximal length. It's at a low possibility of tearing the muscle or tearing the tendon, right? And for the record, there's also joint receptors. There's actually a lot of these. There's actually like a lot of them. And basically their job is to sense like pressure, acceleration, deceleration. and they live within like the joint capsule, and they're experiencing the when your joint like collapses, it's like woof, there's a lot of pressure in there. It's like a balloon being overfilled, or like their job is to like sense like, oh, the cartilage just got smacked, right? There's like little nerve endings in there. There's a lot of them. There's sort of like 4 main ones that we're seeing here, but those joint receptors, they sense pressure, acceleration, deceleration. They sense when your joints are moving. So when I was talking about proprioception earlier, these 3 mechanoreceptors are what give us our proprioception. So again, when we go back to like the idea of building a very stable athlete, we do that by training in a maximal sensory environment, aka a very wobbly environment. Or sometimes you'll hear us say a proprioceptively enriched environment. You know what a proprioceptively enriched environment is? It's the difference between this and this. This is proprioceptively enriched because now I have to balance while I'm standing on one leg, right? That's proprioceptively enriched. It's where my muscle spindles are being like, we're at this length. Oh, no, we're not. We're over here. Where are we? Like it's where my Golgi 10 organs are doing the same thing. And then the joint receptors, right? Early stage improvements when it comes to like your clients getting like better at stuff. It's so funny, guys. Like you'll be training your clients and they'll totally like improve like a little bit. Like you'll take them from workout 1 to workout 2 and they're just way better in like just that short amount of time. And then like, they've been training for like 2 weeks and they're like, I feel so much stronger. I feel so much better at this. This program is working. Look, here's the thing. Yes, it is. And they're like, I feel like I can see more muscle. It's like, in 1 to 2 weeks, probably not. But, I don't want to yuck their yum, like, so we'll say like, it's like, yeah, like you're definitely like improving for sure. We can see it. It's not so much because they're building massive amounts of muscle in 1 or 2 days. It's that they are experiencing changes in their nervous system. Their nervous system is finding a more efficient path or an easier way to recruit a muscle fiber. And it's just getting a little bit better at the movements, which results in more strength. Again, if your client can do a single leg bicep curl, I promise you they can do a regular bicep curl. Whew. So that is this nervous system, which obviously always takes the longest. Any questions, comments, or concerns on that, guys? How y'all feeling?
Back to the how do you say it?
Pedometer?
Oh no, not the pedometer. When we were talking about the ankle stretch.
The anterior translation, posterior translation. Yeah, impingement.
Impingement, yeah. So like, I guess I have bad impingement because you've seen it. Like sometimes
you got the tight ankles for sure.
So sometimes like I'm gonna be a little off though. So as a trainer, how am I gonna know what's the proper way to like stand?
Well, I mean, honestly, that's something you can start working on now, right? And do you feel a pinch in the front of your ankle, Simon, when you stretch your calves?
No, but I do remember when we were doing the box jumps, I couldn't land on a flat foot.
Yeah, well, you got tight calves, right?
Yeah.
So here's the thing. If you don't feel the pinch sensation, it doesn't necessarily mean the bones are out of alignment, but we absolutely know that you've got the tight calf muscles, right? So what's happening is like, we got our gastric nemus and our soleus here. These are the 2 muscles in your calf that are probably, responsible for all that tightness. And they are responsible for plantar flexion, right? They're the ones that are doing the toe point. So you're really good at this, but you just need a little bit more of this. So what you need to do is loosen up this side of the joint by stretching out those gastric nemus muscles, and then activate the anterior tibialis muscle, which is on the front of the shin here. So like these muscles on the front, that does the dorsiflexion, pulls your toe this way. So you need to strengthen your anterior tibialis and loosen your gastric nemus and your soleus. And you can do that through like stretching your gastric nemus and soleus. So for those of you guys who have been with us for a module, you might remember that we talked about autogenic inhibition, where you actually stretch the muscle for a full 30 seconds. You do a static stretch, right? And what happens when you do big, long static stretches is your nervous system goes, holy crap, we are at maximal length and we are at maximal tension. This muscle is going to rip off the bone, right? And it kind of panics, right? And that's why when you're stretching, you feel that tension. You're like, it kind of hurts, right? So you put it in that position, not enough to actually freaking tear it. Please don't overstretch, but like pull it into an uncomfortable position and hold for a minimum of 30 seconds. And when you do that, your nervous system is going to go, all right, apparently we are not letting up. We are going to be in this stretch position. We're not letting go. Safest thing to do is to relax the muscle. So then any of those fibers that are just passively contracting 24 hours a day, 365 days a year that are making you really tight, Simon, what is going to happen is your nervous system will say, all right, inhibit those, turn them off. They're contracting as they think they're protecting the muscle, but that will cause them to relax, because that's the safest course of action. By lengthening this, we'll have more length, which will take the tension off of the Golgi tendon organs, right? So by holding it for 30 seconds, autogenic inhibition says relax. So it'll relax the whole area and you'll get to full length. So do those big, long static stretches, particularly this one, the runner stretch, where you are driving your back heel down with a straight leg. That's going to be really good for the upper calf. That's your gastric nemus. And then when you're doing your soleus, the exact same thing, except bend your knee. By bending the knee, you'll put the stretch on the soleus. And then follow that up with, come on. Internet, you're failing me. This one, where you actually sort of like collapse down, plant your heel super solidly on the floor, don't let that heel come up, and then just bring your knee as far past your toe as you can get it. And that'll be another really good soleus stretch. And if you have to do that with a band, you can, but if you don't have the pinching sensation, you don't need to. Yeah, there's somebody using a kettlebell. It's like a combination of, this is very popular among squatters. So do those. And then once you're done with all those stretches, follow it up by strengthening your anterior tibialis by doing the resisted dorsiflexion. She's moving a little quick for my taste. Bring it up for 1, hold for 2, and then bring it down slowly, kind of like that. And that's your key to getting better and better and better at like all of that dorsiflexion stuff. And that will help you squat deeper. Start that process now. And by the time you get out there, you're gonna be able to show your clients and be like, hey, like this is my posture thing. You know, you're probably not gonna be done with it. This probably, like you got this way because you probably have some type of habit in your life. I don't know if you're maybe a foot bouncer or maybe you just hold a lot of tension. You could also just have, unfortunately, dude, some people like have really short tendons in certain parts of their body. It could be genetic, you know, you come from a long line of tight calfers, you know what I mean? But something is happening, but you'll get better and better and better at it. And then you can show your client and be like, hey, watch, when I do squats, you'll notice I tend to rock back a little bit because my ankles are so tight. And then you look at your client and go, your problem is that your knees buckle inwards, right? Or your problem is that you do this, you do that. Everybody's going to have different postural stuff. Me, I got really tight hamstrings. Like my hamstrings are super tight. So they pull my butt down in the back. And then also my ab, I tend to hold a lot of tension in my stomach as well. I'm just like, ugh. I'm always like that. And so that actually pulls my pelvis up. So I have a posterior pelvic tilt. This looks like this. It's the butt rounded thing, the butt tucking. So this thing here, right? My pelvis tends to tuck as well. Other people, they get the Instagram booty, right? They stick their butt out. That's tight hips and tight upper back. Flip it for me, tight abs, tight hamstrings. Everybody's gonna be a little different. But yeah, does that answer your question?
Yeah, thank you.
Yeah, throw it into your routine every day. You know, I never work out. even if it's upper body day. If I was doing shoulder day, which I don't have a shoulder day, if I was doing shoulder day, right, I would stretch my hamstrings.
All right, cool.
All right. For the record, by the way, like all that anatomy stuff, like that comes around in our assessments class. So next module in about 6 weeks time, guys, we are going to spend a lot of time having conversations like that one. Okay, so let's take a look at the skeletal system here. So it is our framework, right? It is what gives our body all of its structure. As we're looking at it, it acts as like the resting ground from all of our muscles. It allows our muscles to have something to manipulate. It makes these big long levers that sort of allow us to sort of move things around, right? So it's going to be made up of your skeleton, yes, your bones, right? But it's also made up of like all of your joints and all of your connective tissue that live within those joints. So when we say skeletal system, we say bones, joints, and connective tissue. So you do have some different divisions here. You've got your axial skeleton that houses your major organs, as probably the most important of which is your friggin' central nervous system, right? So that's your skull, it's your vertebrae, and it's all of your rib cage as well. But you've also got your appendicular skeleton. That is your arms and legs that allow you to, like, you know, sort of move around the world, right? So your pelvic girdle and your legs, that's your appendicular skeleton. Your clavicle is your collarbone, plus your scapula, and then your arms. That is also your appendicular skeleton. So your bones are constantly remodeling. They are constantly going through like this big long growth because they're very hard tissue, which means they experience like chipping and damage and like little tiny microfractures and things like that all the time. You know, the harder the tissue, the more likely it is to sort of like chip and stuff. My roommate loves when we moved in together, it was so funny. Like I hate ceramic plates. I hate them. They're thicker. I'm always nervous when I'm putting them in the cupboard that they're going to chip because they're just, they're this hard tissue, but ceramic like chips and stuff. I prefer like Corelware, you know, like where it's like still also very kind of ceramic feeling, but like practically indestructible. So I'm always nervous that I'm going to like chip something while I'm putting it into the cupboard. That's kind of how your bones are, honestly. Like they're porous, they're holy, you know, they're not as tightly, you know, they're not fully like solid. In fact, they kind of have this honeycomb shape, you know. This is what your bones actually look like when you zoom in, you know, it's this kind of interesting sort of honeycomb shape that we're seeing there, right? And so that is very likely to experience little microscopic itty bitty tiny fractures, which means we need to constantly repair any of that damage. So our bones are alive and constantly going through a remodeling process where they are breaking down any imperfect, damaged bone tissue and rebuilding it into like stronger, more damage resistant bone tissue. So we have specific cells that are responsible for that. We've got our osteoclasts, which are, you know, the deconstructors, right? They're coming in and tearing out the old tile and the old kitchen cabinets and things like that. They're responsible for breaking down the old bone tissue. And then you've got your osteoblasts, which are responsible for putting in the new cabinets and like putting in the new tile and like building everything up and doing the remodeling, right? That builds us up. So when osteoblast activity, the bone building, outweighs osteoclast activity, bone breaking, our bones will grow and increase in density and strength, making us more resistant to damage in the future. And that's why exercise also increases bone density. When we're kids, our osteoblasts, our bone makers, they are super, super, super active. And when we're adult, seniors, our osteoclasts become more active. So that's why it's so important to take advantage of it as a kid and make kids work out a lot and exercise regularly, because that will increase that activity even further and make even stronger bones. We take advantage, right? We're playing to the strengths of their biology. And then as seniors, we're sort of like, you know, playing against their weaknesses, right? Unfortunately, their osteoclasts become more active. But if we can exercise regularly as a senior, that will say, hey, don't break down this bone tissue. I use that stuff, you know? And that will sort of like, hopefully keep it around longer. So as we're looking at bones, we got a couple different types. We've got long bones. They are long. Shocker. We got short bones, which are sometimes called cuboid bones. These tend to be a little bit shorter and similar. And like carpals of your hand, for instance, are a good example of this. They tend to be kind of like in your ankle, kind of cube-shaped bones. And then we've got flat bones. Flat bones tend to be very thin and kind of protective. Your scapula, your pelvis, even your sternum would be considered like a flat bone, or your patella, right? It kind of protects the kneecap. Well, it is the kneecap, but it protects the rest of the knee. And then we've got like, I love this. It's like scientists were just like, you know what? Labeling the types of bones, not important. The rest of them are just going to be irregular bones. And, they're the weird ones, right? Like irregular bones are just like the very uniquely shaped bones that have sort of a unique function, right? Like, when you look at your vertebrae, it's got all these little itty bitty tiny teensy weensy muscles that are sort of covering and keeping it, right? They have all these like special markings so that those muscles can be there to create stability to keep this whole thing in alignment, right? And it's very important that it stays in alignment because your nervous system runs through it, right? When we look at our vertebrae, right, it's got all these little like processes that make it very good for muscles to attach to. It's got this little section here, the body that actually allows like your spinal discs to sit, and then that soft tissue keeps them from collapsing on themselves. And then they get these little facets which allow them to link together. And then there's a central canal that runs through all of them, a little hole in the middle that protects your nervous system. Huge, right? Very, very cool. So, all of your bones are going to have special types of markings on them. They're all going to kind of share this thing. You just heard me talk about one of them. There are what are called processes, okay? Processes are little projections from your bones, right? That allows your muscles to get a really good grip. So when you look at your vertebrae, right, you can see there's a bunch of different processes on there, right? Opening that up a little bit better, right? So you can see a process here, a process there, right? All of those processes allow good connections to occur between like all of those little tiny muscles. So when we look at depressions and processes, right? Depressions are little indentations on the bones, and processes are little projections from the bones, right? So when you look at your bones, you'll notice there's all kinds of like weird little ridges and depressions and stuff like that, right? And it allows like a muscle to have a spot to kind of grip onto. I'm looking at a lot of like depression pictures here, right? Actually, your skull is a very good example of this. I don't like to use the skull because it's not super relevant to us, but you can see like, look at all these like interesting little like, processes and or not processes, but like depressions, right? It allows you've got so many face muscles and all of them can kind of contort. They're all pulling and they're using their little grips, right? So, here's a little process that allows like your glute muscles and TFL and hip flexors and stuff to have a grip, right? Here's a little tubercle, which is like a depression that runs down, and that allows like your quadriceps to kind of sit into, right? So there's all kinds of very, very interesting little processes and depressions out there. We don't have to have them memorized or anything like that, but understanding a little bit how they function is always helpful to understand like how our muscles are sort of recruiting to actually produce that movement. So those are your bone markings, right? We got different sections of our vertebrae. You can see the cervical, thoracic, lumbar, and then you get your sacrum and coccyx down here. And that's where all of those, peripheral nerves are sort of branching out from. And then lastly, we've got our joints, right? So we're looking at joints. Obviously, there's all kinds of them, right? These are the structures where one bone is sort of meeting with another. We call that an articulation. They're articulating with one another. There's like to thread my knuckles in. That makes like a really good, like strong connection there. This would be like a really good example of like a gliding joint, right? So there's three main joint motions that are going to occur. Either one joint surface is going to roll over another one, right, like this, or you're going to see a sliding action like that, or you will see a spinning action like that. So those are sort of the three main joints. movements that we've got, we call those our arthrokinematics, which is my least favorite definition in biology. It means joint motion, which literally the definition is shorter than the freaking word. So why do we have that word? But arthrokinematics literally means joint motion, right? Arthro for joint and kinematics for motion. So the three main types that we'll see are rolling actions, sliding actions, and spinning actions. And then there's lots of variations of joints doing those various actions, right? So the two major categories of joints are synovial versus non-synovial, right? Synovial joints are what you think of when you think of a joint, right? That's the one that has like a joint cavity, full range of motion. It can make the rolling, sliding, or spinning, or combinations of those movements, right? Like hinge joints can really only do a little bit of rolling. They might slide just a little bit, right? Like your femur, for instance. If you ever look at like femoral movement, it makes a little bit of both of those movements simultaneously. That's not helping. There we go. So you can see how it does kind of both those things simultaneously. So you can see a little bit of like, there's a little sliding that happens, but it also like does like a rolling action as well. So that is sort of a combination of those two coming together. So synovial joints are like fully movable joints. You've also got non-synovial joints. These are like little to no movement. Cartilaginous ones, maybe a little bit of movement. And then you get fibrous ones that like no movement. They're basically just like a solid bone. But like I said, we're gonna spend most of our time talking about synovial joints, right? Synovial joints, fully movable. They have a big old cavity. The more space in the joint, the more mobility it has. That's why a ball and socket joint is so very mobile. But one of the problems with increased mobility is decreased stability. So unfortunately, this is one of our most commonly dislocated joints as well. They also have a lot of fluid in them to sort of like help with that friction because they are moving so much. They need to be able to deal with friction because like, you know, they're going to grind and rub and stuff. That's why they produce synovial fluid. And there's a lot of cartilage and bursa and things like that. So bursa are these little like fluid filled sacs that live within your joints, right? And their job is to like embed themselves in connective tissue to make sure that like, you know, a muscle isn't going to rub and get like too much friction on a bone, or two bones aren't going to rub and get too much friction on themselves. So you can get a condition called bursitis where you might actually rub this a little bit too hard and then that fluid filled sac either bursts or it will get inflamed. And then that causes like a lack of space. And then that lack of space makes your joint feel weird. And you're like, God, and you know, you start to feel sort of an ache or a pain. And you're like, is that a joint? Is that a muscle? Like what's going on there? Well, it's like kind of where the muscle is interacting with the joint. So there's all kinds of specialized structures within synovial joints that eliminate and reduce friction and allow you to sort of move effectively. But then there is the connective tissue, and I would consider all of that connective tissue, right? So one of the most important types of connective tissue found within your skeletal system are going to be your ligaments, right? So ligaments are the connective tissue that provides stability, and then they hold your bones together, right? So like this right here is holding the femur to the fibula here. That is what's known as your LCL, or lateral collateral ligament, right? And so it's attaching this to here, creating some stability, but it's almost like duct tape, you know? Like it's stable, you know, duct tape's amazing. It holds the universe together, but like, it's not exactly like the most stable, you know, it's still like terrible, you know? Terrible, not terrible. It is able to like, you can tear it in half. And so like, yeah, it's fairly solid, but like, these are why like our synovial joints are the ones that we usually have like joint problems in, you know? So they're there to provide like stability and also proprioception to your nervous system. Your nervous system is going to get information from your ligaments saying like, hey, I'm overstretching. You're going to roll the ankle. You're going to tear me, you know? And so like that's going to change how your body moves. So these are specialized structures that attach bone to bone. Now, I love and hate this picture because this is a very good picture of a ligament. You are going to see it again in this PowerPoint. There is also a picture of a tendon here, which looks the same as the ligament. This is muscle to bone. That's a tendon. Don't get them mixed up. Bone to bone, ligaments, muscle to bone, tendons. All of your muscles end in a tendon. Your bones will be connected via ligaments. The reason we draw them both in white, the reason they look very similar is because they both have poor vascularity. They just don't have very much blood flow going to them. So because of that, they repair very slowly. They are often the tissues that get the most damage. This is why there are so many problems with like ligaments and tendons. Tendinitis, for instance, or like bursitis, if you're dealing with like a ligament, or like a rolled ankle, you know, like tendinitis is like a very common problem where like the tendon is just getting overworked by pulling on the bones. Well, you can also sprain your ankle or sprain your knee. That's where you are experiencing like a ligamentous problem, right? It's a ligamentitis, you know, but that's not a term. So that is your skeletal system in a nutshell, guys. I will say when it comes to increasing bone density and keeping your bones healthy, one of the most effective tools in your arsenal is to ensure that your bones are working against gravity as a resistance. There's something special about gravity that is going to be weight-bearing exercises. Exercise that works against gravity. Running is a good example. Lifting weights is a really good example. Body weight exercises are obviously a good example. All those are great. They have been shown to be the most effective for your skeletal system. Now, swimming and cycling, which are both great forms of exercise, make no doubt about it, actually haven't been shown to have as much of a positive impact on your skeletal system because they're using like resistance, you know, like a rubber band would be a good example, or just like the friction of the wheel or the friction of just like the viscosity of the water. Those things are really good and they burn a lot of calories and they're incredibly good for you in general. But if you had a client with bone density issues, we would actually put the emphasis on these other types of cardio and these other types of like exercise. They're very good at helping us maintain bones. So questions on the skeletal system before we sort of wrap up with the muscular system here. Questions, comments, concerns? How's everybody feeling?
Good. Good, thank you.
Love that. Thank you. All right, let's go ahead and do the muscular system. So muscular system, we do know, is a series of muscles. Each of them is technically, by biology standards, their own individual little organ. And they all kind of come together to manipulate your skeletal system in various different ways. You get about 206 bones in the body. How many muscles do you have? I don't know. Somewhere around 500, maybe around 700. Depends on who you ask. Some muscles, you know, you look at your biceps, you look at your hamstrings, for instance. It's made up of your biceps femoris, short head and long head. Is that two muscles? Is that one muscle? Kind of depends on who you ask, you know, like there's really no kind of clear thing. You've also got your medial hamstring on the other side, which is your semimembranosus and tendinosus. Is that one muscle? Is that two muscles? I think it's two muscles. I don't know, you know, like, so is this 1, 2, or is that just one? Is that two? Is that just one? You know, we haven't been able to get to a place where we agree on this stuff yet. But either way, the one thing that we do know is that your muscles are really cool little organs that are able to generate their own internal tension and shorten themselves, which will drag around your skeletal system. That is happening in every one of your muscle cells that make up an entire overall muscle. Your muscle is this really neatly tied together sort of compilation of all of these individual little muscle cells, or what we call muscle fibers. We call them muscle fibers because they have little contractile proteins that we don't really see in any of our other organs. So it is a compilation of individual muscle fibers neatly wrapped together in bundles. So a muscle fiber is an individual muscle cell. When you wrap a whole bunch of muscle cells together in a bundle, we call that a fascicle. And what a muscle is a bundling of fascicles, right? So all of that kind of comes together, and then it ends in a tendon, right? The tendon is the connective tissue that's attaching your muscle to your bone. Now, again, I hate this photo. Because this kind of gives you the idea when you look at this that the quad tendon hits this bone here, and then there's a separate tendon attaching this bone to here. It's all technically one tendon. What it actually looks like is this. See how the quadriceps tendon actually goes over top of the patella and then inserts here? That's the actual freaking tendon. It's not ending here and then picking up down here. Honestly, this picture is so much better than the one in our PowerPoint slides. So you can see there's the tendon, right? Looks very similar to the ligament over here. That's the LCL ligament we were talking about a minute ago, right? Bone to bone, muscle to bone, right? So tendons attach your muscles to your bones. They end. There's all these like little collagen proteins that kind of come together to create this really stiff material, threads into all the muscle fibers, threads into all the bone, and allows that connection between the two. This is how your muscles drag around your bones, right? So your tendons, again, we draw them in white because they don't get very much blood flow. They repair very slowly. This is why tendinitis is such a very common problem. So now you can kind of see here is an overall muscle with its tendon attaching it to a bone, right? And all of the fascicles making up that muscle, right? So, this is like, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 little muscle fibers, kind of coming together. Fascicle, 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 fascicle. All these fascicles kind of bundled up to make up the overall muscle. So then if you look inside of a fascicle, you'll see it's, a whole bunch of individual muscle cells. So muscle cell, muscle cell, muscle cell, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 muscle cells here, right? We pull one of those muscle cells apart, and you'll notice it's got these little rods with little dots on that run through it. Those little rods are where the magic of contraction takes place. So this little muscle cell, which has all these rods running through it, those rods allow this muscle cell to contract. And if this one contracts with all these other ones, the entire fascicle will get shorter. And when that fascicle gets shorter, if it happens in all the other fascicles at the same time, the entire muscle will shorten. And that's what a contraction is, right? So when we look at a muscle fiber, an individual muscle cell, it's got those little rods that run through it called myofibrils, right? A myofibril is this big long rod running from end to end in our muscle, right? And it looks kind of like that, right? Now, that rod sort of zigzags, right? Like when you were putting it together, it was sort of zigzagging back and forth with all of these little individual proteins. And so it's sort of doing this zigzagging action back and forth, all kind of connected, right? So all of those myofibrils, those big long rods, have these little individual proteins on them, and those individual proteins are what create the actual contraction. So a myofibril are little rods of a muscle fiber that contain your myofilaments. Those are the little contracting proteins, right? Actin and myosin. So here you can kind of see a better picture. That's not maximized. Here you can kind of see a really good picture of like, a rod, and it's got little sections making little zigzags, right? That gives it stability. And then you'll notice that like this little section right here, right? It is sort of divided into little sections. So each section is called a sarcomere. Think of it as like an area of town, right? It's the area of like a myofibril. So there's a section, right? So those little like sections house the little proteins. And when we zoom in like crazy on those proteins, man, this is a really zoomed in picture. You can see there's the really thick rod in the middle and then the really thin rod on either side. The thick rod has all these little heads that grab the little thin rod. And what that does is that allows this sort of sliding action to occur where the muscle fibers slide into one another like this, right? So here, when you look at the individual little sarcomere, right? This little area from here to here, right? We're just looking at where they're sort of crossing over one another, right? So what's going to happen is, actually, you know what I can do? So when we look at this like little section, right, what's going to happen is this is going to contract down this way, and this one's going to contract up that way. And that's going to happen over here as well, right? You can see there's the next little sarcomere, there's the next one. And so what a myofibril is it's just a whole bunch of proteins all stacked end to end like this. And so all of them are sort of shortening simultaneously, and that's going to shorten the overall muscle at the exact same time, right? So that is sort of the contracting shortening action that is occurring in every sarcomere along the myofibril, in all the myofibrils in the muscle cell, in every muscle cell, in every fascicle, in every fascicle, in every muscle. Whew! Right? So sarcomere is the little unit where all of this is happening. It's the area with all the little like thick heads grabbing the little thin heads to allow the sliding action to occur. So actin's the thin filament that has all the binding sites, and myosin's the thick filament that does all the contracting. So when we look at that sort of happening all at once, it kind of looks like this. That's not a real GIF, is it? Right? It kind of looks like that. It all kind of slides together. Look, each of these is an individual little sarcomere. So sarcomere, 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 right? And they're all kind of pulling together. And that's happening over here on this side. That's one we're zoomed in on a myofibril here, right? So it looks like this. Look at those friggin' millions of little proteins, right? There's tons of them. And then the crawling action, I do want to sort of, oh, there we go. Well, that's kind of nice, right? So we sort of zoom in there. So we sort of like take an individual muscle cell, sort of look at all the little rods there. And there's other ones, right? They're all sort of like lined up next to one another, and they just slide like that. They sort of just pull down on one another, creating this sliding action. And it's sort of a crawling action. Like what's really happening is it's sort of crawling. You know, the little heads are sort of pulling it forward. They're kind of pulling like hand over fist, you know? And so like they pull kind of like that, right? Head reaches up, grabs it, slides it, head reaches up, grabs it, slides it, right? And that's all taking a ton of energy, right? So when we look at that like structure, we do need to have a way to get those muscles to relax so that we, stop the contraction. That's where troponin and tropomyosin come in. These are regulatory proteins that block this action from occurring. They're there to like kind of get in the way and keep the muscle from contracting. And then one other piece of like information, honestly, I don't think you guys will be tested on this, but it's in here. You also do have like what's called a Z line, and that's what's creating the little zigzag action. Each sarcomere, rather than lining up across the rod, sort of zigzags like that. They sort of like create this little zigzag action. That just creates stability, rather than like having it all, then it would sort of like fall apart laterally. By zigzagging it, it can resist, pressure this way and this way. So yeah, when we're looking at creating a muscle contraction, what's going to happen is you're going to start with neural activation from the nervous system. So your nervous system is going to recruit the right number of muscle fibers. It does this through like an organized setting called a motor unit. So what you have is you have one neuron that zaps a whole bunch of individual muscle cells, a whole bunch of individual muscle fibers to create that contraction, right? So what'll happen is like you know, it'll go this way, down here, and then it spreads out and zaps all those fibers. So when we look at a motor unit, it's one individual neuron, and it comes down and just threads into all of these individual fibers, right? Look at all the little heads, right? Like this, each one of these is a muscle cell with all these little individual like proteins in it, right? And there's just a little bit of a fiber there for every one of them. So a motor unit could recruit thousands of muscle cells, right? And that's actually what you do. You might use like 10,000 muscle cells to recruit something in your glute because your glute's really strong. Or you might recruit a couple hundred to move the muscles of your eyes. Very, very different contractions there. So a motor unit is one motor neuron and all of the fibers that it sort of deals with. So here is neural activation from start to finish. You don't actually have to be able to describe this whole process, but just so you guys know how it works, right? So an electric impulse is going to travel from your central nervous system down the axon of a neuron, and then it will get to the end of that axon where it will release a neurotransmitter in between the neuron and the muscle cell. That neurotransmitter is going to be acetylcholine. So acetylcholine is going to work its way across the neuron, bind to the muscle cell. That is going to trigger the muscle cell to run electricity across its body, which will release calcium into the sarcomere, into that whole area. So then all that calcium comes in, right, flushes in there. And when calcium flushes in, it moves those two regulatory proteins that block the binding sites. It moves troponin and tropomyosin out of the way. So they move the chaperones out of the way. And then your muscle fibers, myosin's little heads, will burn up a little bit of ATP to reach up and grab actin and drag it towards the center. That's the sliding action that occurs. So the entire sarcomere will shorten, where you're pulling this Z line this way and this one this way. So the entire thing shortens down. These little heads reach up and grab their little binding sites. So, and then when that contraction is over, calcium will get flushed out of the sarcomere. The chaperones, troponin and tropomyosin, go back into place, forcing it to unbind with the actin, and that ends the muscular contraction. Whew, that's complicated, right? Like, that is a lot. But that is how muscle contraction. So there is a lot of chemistry taking place here. So now, if we understand some of that anatomy, we understand how that functions at like a very tiny cellular level, now it can affect our training. Now it can affect like our sets and our reps and stuff, right? Because here's the thing. If I want to create like a big, powerful contraction, you know what I need? I need more myofibrils, right? So there's actually two ways to grow a muscle, to make a muscle a little bit. Actually, there's really three ways to grow a muscle, right? So what we'll see is the difference between what is called sarcoplasmic hypertrophy, which is making the muscle cell larger and pumping a bunch of more fluid into it, and myofibrillar hypertrophy, which is making more of those little proteins, making more of those little muscle fibers. So let's say you've got a muscle fiber here. It's got 4 proteins in it and about this much space in terms of cellular fluid. Now, if you made that muscle cell larger and there's more fluid in there, that's great, because that means that muscle is going to be stronger because it can produce energy more frequently, right? Remember, we produce energy in the fluid of our muscle cells. Some of you guys know that. Some of you, I haven't been over that just yet. It will come around in a couple of days when we get to metabolism. But more fluid means more contractions. It means you're a stronger person, right? So this is muscular because of a bigger muscle cell with more fluid to kind of pump all that stuff in there. But one thing you could also do is just make more proteins, right? Look at all this, make more proteins. And now we call that myofibrillar. We have more myofibril. We don't have quite as much cellular fluid as well. But like when you can get to a place of doing both of these things simultaneously, that is how you make muscles way bigger, right? Now there is also a little bit of hypertrophy. This is very little bit that can occur by making more mitochondria. Remember, mitochondria are the energy producers as well, right? You either produce energy in the fluid or produce energy in the mitochondria. So you can shove some mitochondria in here as well, and that will also make the muscle cell bigger. But the effect is very small. And that is why there's a difference between type 1 muscle fibers and type 2 muscle fibers. So when I say that, what I mean, and you know, so when we look at like type 1 versus type 2 muscle fibers, you'll see there's a big difference between some types of athletes, right? You'll see that some, oh my God, I can't believe I'm not seeing a picture of this here. You'll see there's a huge difference between like a sprinter and a marathoner, right? Look at the difference in like these two bodies here, right? These are probably both like world-class athletes, but they look very different from one another, right? So the one over here, that's very much type 1 muscle fibers. We call those slow twitch fibers. These are the ones associated with like endurance, right? And then over here, we got our type 2 muscle fibers. Those are the ones associated with strength. So type 1 fibers are slow twitch. They have way more blood flow going to them. They have more mitochondria and they have more myoglobin. So the way that those muscles got big is because they're probably packed full of mitochondria, maybe a little bit of cellular fluid, but they don't have very many rods, very many myofibrils running through them, which means they are much smaller in size and they can't produce as much force. These are very slow to fatigue muscles, but not very big muscles. So these are like stabilization or endurance type fibers. Your core muscles that are keeping you upright right now, those are mostly slow twitch fibers. We want those to be able to work all day. Your heart is like the slowest of the slow. You know, it's not lifting any dumbbells, but it literally starts contracting before you are born and will continue contracting until you are done on this planet, right? It never stops. 24 hours a day, 365 days a year. That is the ultimate slow twitch endurance type fibers, right? The ones that David, you were using this morning to go for a run, those are very much your type 1 muscle fibers. They're not going to make you big, but they're going to give you plenty of endurance, right? Now, fast twitch fibers, those are type 2. And they have way less capillaries. They don't need as much blood flow because they can produce energy within themselves, right? They got a lot of cellular fluid. They can just take glucose and spit out energy, right? They don't need to have oxygen delivered. They don't need to use their mitochondria. So there's a lot less mitochondria. They need mitochondria, but there's a lot less, right? And they also have less myoglobin because myoglobin carries oxygen around. If they're not using oxygen, why have myoglobin, right? These muscles tend to be larger in size. There's more myofibrils running throughout them, or there's just a lot of cellular fluid. They produce more force because they're just bigger and stronger, but they are very quick to fatigue. You know, you're not doing a lot of repetitions with your big, strong muscles, right? I'm not deadlifting for as many steps as I'm taking on a 3-mile run. You know, like, you know, I get like, what, you said 10,000 steps in a day, you know, like I'm not doing 10,000 deadlift reps in a day, you know, at my 1 rep max. So they're very quick to fatigue, right? These are used for your short-term force or power contraction types. Now, there are 2 sort of subcategories here. There's type 2A and type 2X or type 2B, sometimes you'll hear them called. Type 2A are the true, or sort of the stopgap between like fast and slow twitch. So like type 2A is like, we call that fast twitch because they are big, but they're high oxidative fibers, which means they have a little bit mitochondria, they have a little bit more oxygen delivery. These are usually the ones that you think of when you think of like field-based or court-based sports. It tends to be athletes who are like strong, quick, powerful, but they also need to be able to play like, you know, a full game. So they have a little bit of endurance, right? That's type 2A fibers. They're big, but they're not like massive, right? Then you have your type 2X fast twitch glycolytic fibers. These are the true fast twitch fibers. These are super explosive. When you think of like an Olympic powerlifter, or like an Olympic sprinter, right? This is all type 2X fibers. If this guy is like 100, you know, actually, let's pull up, where's Bolt at? Usain Bolt, right? Very, you know, you can see his muscles are like much like larger than over here. Both these guys, these are the two best runners in the world right now. This is Eliud Kipchoge on the left, and we got Usain Bolt on there. Fastest man on the planet, fastest man on the planet. Different athletes though. Fastest in the 100 meters, fastest in the marathon. So like this guy is the fastest over 100 meters. This guy's the fastest over 42,195 meters. 100, 42,000. Type 2X, type 1. And then you got like, you know, probably like who's got the world record today? Is that this guy here, who's a little bit even bigger than Usain Bolt? I'd say like a little bit larger. That's the 800-meter dash, right? That's like right in the middle. He's not as fast over like a super short term, but like he's not as, you know, he's not going to be like a long distance runner either. I would associate that with being like an athlete in like a basketball or football or something like that. That's like sort of a type 2A situation. Like, you know, I love my guy DK Metcalf. I love him. You know, I'm a Seahawks fan. He wanted to like see, you know, he's got a super fast 40-yard time. He's humongous. He's a big dude, and he tried to compete in a 100-meter dash as fast as possible. He did really well, but he is a type 2X athlete, and he is trained for 40 yards, which is not the same as 100 meters. So he's really good at that, but he's not going to set any world records here. You know, he tried to qualify as like an Olympic runner, but like, unfortunately, they're just different sports. You know, the endurance that he has to play several like, you know, quarters of football is dragging him down from being able to like be a true type 2X athlete that you would see in like a 100-meter dash. World class, you know, but just different strokes for different athletes, you know. Now we've been talking a lot, you know, Simon, we were looking at the calf stuff, right? And I kept saying, these are the muscles you need to strengthen. These are the muscles you need to stretch, right? So the reason we know all that is true, this is one of the other things about your muscles, is that they are arranged in such a way to only pull. Muscles can pull and they can relax, which means we have to have another muscle on the opposite side of the joint. So when we're looking at how our muscles are organized, we have muscles that are considered agonist muscles. These are the prime movers for a movement, okay? These are the muscles that are primarily responsible for contracting whatever joint action we're talking about. If it's elbow flexion, the prime mover is my bicep. If it's elbow extension, well, it's going to be the opposite muscle of flexion, right? Flexion is the opposite of extension. Extension is the opposite of flexion, right? So if I'm talking about hip extension, my agonist muscle is going to be my gluteus maximus, right? Which means, what's the opposite of extension? It's flexion. So what muscle does hip flexion? Well, that's my hip flexor complex, my rectus femoris, for instance, which is this muscle on the front of the hip. It's one of your quadriceps muscles, right? So that is antagonistic of my hip extension. So we would call that muscle an antagonist if what we're describing is hip extension, right? So an agonist is the main muscle for whatever particular movement is we're talking about. During a push-up, the agonist is my pectoralis major. During a squat, the agonist is my gluteus maximus. It's the main primary muscle. Then you've got synergists that work with your agonists, right? They help out, right? So my hamstrings assist my glutes, right? The erector spinae erects me upright while I'm squatting. They're there to help. Then we've got antagonists going exactly in the opposite direction. Antagonists work opposite of your prime movers. My hip flexors are opposite of my hip extensors. My hip flexor complex is the antagonist to my gluteus maximus. My triceps is the antagonist to my biceps. But likewise, my biceps are the antagonist to my triceps. So when I told Simon, when I was saying like, hey, stretch out your calves, that's your gastric nemus and your soleus, those are muscles that are working too much. So we need those antagonists to turn off while your anterior tibialis over here needs to work. So we got to get these guys to shut up. We need to get this one to turn on, to wake up, you know? That is what's going to draw you back to the appropriate, like, you know, full range of motion. Meanwhile, we also have stabilizers. Stabilizers are all the muscles that are sort of stabilizing while agonists and synergists are kind of pulling everything around. So your core muscles, your rotator cuff, things like that, that are sort of holding everything together. And that's muscles, guys. Any questions on muscles?
No, thank you.
All righty. All right, let's go ahead and wrap it up with hormones here. So that, by the way, that's your human movement system. But there is one extra little system that does have some effect here in your endocrine system. Works with your nervous system here, right? So the endocrine system is a series of glands and hormones that also help control bodily functions, right? So like, you know, you got like a host organ that's going to sort of hold on to a gland, and then that gland is going to sort of release whenever it's told to. And now that's in your bloodstream. Those hormones will run around your bloodstream. They'll bind to certain things and they'll trigger stuff to happen. So growth, metabolism, things like that. So here's a bunch of them, right? We got your pituitary gland here in the brain. That's sort of the master gland that tells everything else to sort of, you know, it releases a bunch of hormones that trigger the release of other hormones, weirdly enough. So for instance, this would travel down and stimulate the thyroid. So your pituitary gland releases TSH, thyroid stimulating hormone. That makes your thyroid release thyroid hormone, which then either speeds up or slows down the certain things in your body, right? Pituitary gland might release what's called ACTH, adrenocorticotropic hormone. That travels down, it touches your kidneys. Your kidneys release a bunch of adrenaline. So your pituitary gland is going to do most of that work. So your thyroid, it's going to help with like metabolism, speeding up or slowing things down. You've got your adrenal glands. They create like fight or flight hormones. Epinephrine, for instance, is what synthesizes adrenaline. So when I say that your kidneys, your adrenal glands release adrenaline, technically they release epinephrine, but then it becomes adrenaline. You get your testes, which produce testosterone, as well as your adrenal glands also produce testosterone, weirdly enough. And then you get your pancreas. That's a big one. Your pancreas releases insulin and glucagon. That helps you regulate blood sugar levels. If you have too little sugar in your blood, your body can't produce energy, you pass out. You have too much sugar in your blood, and your body actually can't perform certain physiologic processes because sugar's gumming up the works, right? So we need to keep those levels at a perfectly sort of balanced place. Insulin tells sugar to leave, glucagon tells sugar to enter the bloodstream. So insulin tells your excessive sugar to become glycogen or to become body fat. Glucagon tells glycogen to release that sugar back into the blood. So when we talked earlier about the fight or flight responses or the rest and digest responses, we were talking about like your nervous system doing this. It's doing this sometimes through like a series of hormones. For instance, when you're done exercising, your body will release this hormone called ghrelin. Ghrelin is a hormone that tells you you're hungry. Or it might release like insulin or glucagon, right? So what if it was like adrenaline? Well, that's where you get your fight or flight response, right? So epinephrine or adrenaline increases your heart rate. It triggers the release of glucagon, which raises your blood sugar levels, and it opens up your airways. It actually causes your blood vessels in your lungs to dilate. So when we inject somebody with adrenaline, right, it will actually cause all of this to sort of like open up. So that is a fight or flight response, right? Because your body thinks that it's in danger and it needs to like do all of the like main fighting stuff, right? So there are certain hormones that are both produced by men and women that also regulate growth. For instance, testosterone, estrogen, right? Testosterone, guys are going to produce about 10, sometimes up to 20 times as much of that as women. Testosterone is a very anabolic agent that causes a lot of growth, particularly type 2 muscle fibers. Estrogen, not so much. It does cause a little bit of growth, but it is not quite as like growth intensive. That usually causes much more like type 1 muscle fiber growth. And this is why men tend to be more muscular in terms of muscle mass compared with women. Cortisol, this is a catabolic agent that actually slows things down. This is a stress hormone. We're really glad we produce cortisol because it helps, stress is what allows us to like, be cautious in our life and do things the way we're supposed to. But when we produce way too much of it, it does slow our metabolism down, puts us into fight or flight mode and slows certain things down. A lot of people who struggle with obesity produce massive amounts of cortisol. We got growth hormone, which is an anabolic agent. Both sexes are going to produce that as well. And then thyroid hormone is going to speed up your metabolism. Exercise, by the way, enhances all of these things, which is really great, but we need to make sure that we do it properly, right? We need to make sure that we warm up, exercise, and then cool down. That will trigger the release of like a little bit of cortisol and adrenaline in the beginning. Then we get to work out, which produces more growth hormone, testosterone, and estrogen. And then when we calm down, we do our cool down, that signals to our body, hey, stop producing the cortisol, stop producing the adrenaline. We're done, we're relaxing. And then your body flushes that all out and creates even more growth hormone in response so that you can build muscle because your body knows it's muscle building time. It produces hunger hormones to get you ready to eat, to repair all the damage that you just created. And it flushes all that stress out because it basically is you telling your body, relax, we won the fight. It's okay, we can calm down, right? And that's one of the reasons why cool downs are so important. So, like I said, there are 3 components to the kinetic chain: your nervous, muscular, and skeletal system. Hopefully with that review, you guys feel a little bit more like experts on that area. For my new folks, we will review this literally every module. So you will see some of these PowerPoint slides multiple times. For those of you who have seen it, hopefully that was a good refresher. And for my students, David and Dion, you guys are heading to, I know you guys are heading to Capstone soon. Hopefully you are really feeling like experts. Mo's definitely going to review that with you one more time. But yeah, that is sort of the entire kinetic chain there, guys. Questions, comments, concerns? How you guys all feeling?
Good. That was good.
Love it. So that was our day 5. That is our final lesson for the first half of this class. Tomorrow we'll be meeting up in person. When we meet up in person, we're gonna do a little workshop tomorrow, kind of based around the kinetic chain and stuff. After you're done with like the lesson, whether you go to the morning session or the evening session, we'll either be meeting at 9 a.m. or we're meeting at 6 p.m. But after we're done with that, the test will go up on Canvas. You'll see day 6 available. There'll be a little review video as well as an exam for you to take. And it's going to sort of recap all of the stuff we've been talking about. Then on day 7, that's going to be on Thursday, we're going to move into the second half of class. And we're just going to kind of repeat that same thing. We'll go 7, 8, that'll be homework 1, 9, 10, that'll be homework 2, 11, 12, and that'll be the in-person meetup. And yeah, that's where we're headed. Questions? Feeling good? Cyrus, Danny, how you guys feeling?
Just one question. Yeah. For tomorrow, we have to take something with us, like the notebook, the books or something?
I do like to do a little recap in the room beforehand. So if you want to bring notes, I do find that really helpful. I'll be putting some stuff up on the whiteboard, which will kind of help with all that. So yeah, I do recommend that. You don't necessarily have to drag around too many books tomorrow. I usually try to warn you guys when I need you to bring your books, but bring your Sochi bag with a notepad and paper and stuff, paper and a pen and stuff, and bring your foam rollers and all the stuff that was in your bag. If you can do all of that, because I do like to take you down to the gym afterwards, and we're kind of running low on foam rollers right now.
Okay, thank you.
Gym attires tomorrow then.
All right, we'll see you tomorrow morning.
All right, bro. I'll see you tomorrow night.
Tomorrow morning, yeah, or tomorrow
Yeah,
night.
for me,
Either-
yeah. All right,
either
all right, bye, guys. Bye, bro.
See you, everybody.
Bye.